Okay, so on this video, what I will be explaining is some of the type of nuclear reactions. And just to clear it up, there are 4 types of nuclear reactions. Oh, sorry. There are 4 types of nuclear reactions. One is radioactive reactions. The second one is induced transmutation, nuclear transmutation. Next one is fission and fusion. We will discuss those 3 now on this video, and then radioactive reactions in a separate video. Okay, so let's talk about the nuclear transmutation. It is possible to disintegrate a stable nucleus by striking it with another nucleus. That may be a subatomic particle or an X-ray. So even on his work that Rutherford did about the gold foil experiment, he noticed that when helium was striking the nitrogen nucleus, an oxygen nucleus was formed. So let's see now, an alpha particle, we can say an alpha particle, or we can say helium is striking a nitrogen. So nitrogen is on the 7th place, and the common form of nitrogen is 14. Then we will have the oxygen produced. So if we, and something else, let's figure out this. What is that something else here? Oxygen is on the 8th place, so this something else will be 2 plus 7 is equal to 8 plus that x. From here, x will be equals to 1, so we'll have a 1. And since we are on the first place on the periodic table, because this is telling us what is the number of protons, applying the conservation law of charges, that tells us that we are dealing with hydrogen. And let's apply the conservation law of masses. So 4 plus 14 is equal to oxygen is 17 plus x. And then from here, x is equal to 1. So what you are producing based on this reaction, on this induced nuclear reaction, is so helium is striking the nucleus of nitrogen, and it is producing the oxygen and 17 and proton. Since alpha particle is induced into the nitrogen, then this is an example of induced nuclear transmutation. So let's see another example. An alpha particle is striking aluminum 26. Okay, as a result, new nucleus is produced, and the neutron is produced as well. So you will know that helium 2,4 is striking aluminum, which is in the 13th place of the periodic table. Check it. and it is producing an unknown element with A and Z and a neutron, 1 and 0. Okay, so now using the conservation law of charges, let's find what is this element. So the parent charges are 13 plus 3, and the daughter charges side of the equation are Z plus 0. So from here we find that Z is equal to 15, which in the periodic table is phosphorus. Okay, now let's find what form of isotope phosphorus is. So for that, we will apply the conservation law of masses. It is saying the atomic mass of parent is equal to the atomic mass of daughter, the sum of them. So 4 plus 27 is equal to A plus 1. And from here, we find that A is equal to 30. So what we have is the phosphorus, so 15, 30, which is the same as saying phosphorus 30. So in both cases is the same thing. Okay, so through this method, Enrico Fermi, which is an Italian physicist, was proposing and was able to form higher atomic number than uranium. And those are kind of stable. So this is why they have a place in the periodic table. The way that he did it is he started with uranium 238 and striked it with a neutron. And as a result of this, what he noticed was that there is a uranium 92 to 38 and a gamma ray that is produced. This is the first step. Then this uranium, so uranium 92 to 38, was transmuted into Neptune 93, 239, and an electron and a gamma ray as well. Okay, gamma ray, a photon. And then this 93 to 39 was hit by gamma ray, and then it was plutonium 94 to 39 and an electron as well, and a gamma ray. So if this was the first reaction, then this was the second, and this was the third reaction. So reaction 1 involved a neutron captured by uranium-238, producing uranium-238 and a gamma ray. Uranium-239 is very radioactive and decays into Neptunium-239, an electron and a gamma ray. Neptunium also is a very radioactive and disintegrates under third reaction here into plutonium-239, an electron and a reaction. And this is the final product of this chain. chain reaction or of transmutation nuclear reaction. Okay. Nuclear fusion. Nuclear fission. Okay, let's see fission first. Nuclear fission. So in a nuclear fission, we take heavy elements and break them into smaller nucleus. This process involves bombarding particular nucleus with neutrons. A neutron is captured by a fissible nucleus, resulting in an unstable nucleus which splits. In some process, the binding energy of heavy element is converted into radiant energy. Okay. So an example of a nuclear fission, remember what we said? It's heavy metals. So uranium-92 235 is bombarded with a neutron. And then as a result of this, what it is produced is a barium 56 141, a krypton 36 92. And then if you do the conservation law of masses and conservation law of charges, you will find that actually there are 3 neutrons that are produced and energy. It's a released. A common misconception of fission reaction is that neutron acts like a high-speed bullet entering and exploding an egg. In nuclear reaction, if the neutron is too energetic, it passes right through the nucleus. If the neutron is too slow, it will bounce off the target nucleus. At the right energy level, the neutrons enter in the nucleus and causes this uncontrollable splitting nucleus. Okay, as the nucleus disintegrate, 1, 2 or more, 3 or more free neutrons are released, which then they invade new uranium-235 nuclei. Therefore, this reaction is self-propagating, and it is referred as the chain reaction. Okay, so I will bring a picture here to explain this. So as you see here, a neutron is entering into the nucleus of uranium-92 235, and then it is decomposed into 2 elements, krypton and barium, with different forms of isotopes of those elements. And then as a result of this, 3 neutrons are produced, because when we do the conservation law of charges and conservation law of masses. And then each of those neutrons is entering into the nuclei of uranium-92 or uranium-92 235. And then a chain reaction is produced. But each of them has energy. So energy here, energy here, energy on every step. This is chain reaction, so it is multiplied by 8. If the neutrons are shielded and reflected back into uranium for long enough, and this is about 10 milliseconds, 1 millisecond, the reaction results in an atomic explosion. This is what it is happening in atomic bombs. However, a controlling device can be used to control and reduce the rate of reaction. A stable controlled reaction produces heat that can be used to heat water into steam and then create electricity. The main problem with fission reactors are that uranium-235 is very rare, so you have to enrich uranium. And other isotope forms of uranium, like uranium-238, will not produce a chain reaction. The process produces large amount of deadly radioactive waste, and it needs to be stored very, very carefully. The reactors are subject to human and mechanical failures, which will result into a catastrophic, probably you remember Chernobyl or that explosion that happened in the nuclear reaction of Japan when the earthquake was happening. For the given reaction, so let's calculate now what is the energy produced. Okay. For a given reaction, this reaction that we just have in front, I will bring it here again. So uranium-92-235 plus a neutron will produce barium 56-141 and krypton 36-92 and 3 plus energy. So we'll calculate this energy here. Okay, the energy released due to this reaction, knowing that uranium-235 has an atomic mass of 234. This will be given 9.9934 times U. Barium 141 will be 140.8834 times unified mass, and krypton 92 will have atomic mass of 91.90601 times unified mass. Okay, so now let's calculate the mass of the product and the difference between mass of the product and mass of the reactant. Okay, in the product side, we have two, uranium-235 and a neutron. Okay, so what we will have is total mass of product will be mass of uranium-235 plus mass of neutron. So mass of uranium-235 is given here as 234.9934 plus 1.00. Refer to the table that we had. Okay, 8665 times U. So mass of products will be, let's use the calculator, 236.002065 times unified mass. This is the mass of the product. Let's see now what is the mass, total mass of reactant. of, this is the reactant. Total mass of reactant. This is reactant. Total mass of reactants. Total mass of reactants. So total mass of product will be 1 barium, 1 krypton, and 3 neutrons. Okay, so we'll have barium 141 plus krypton 92 and 3 neutrons, or 140.88340 times unified mass plus 91.90601 times unified mass plus 3 times 1.008665 times unified mass. So mass of products will be, use your calculator, and I have here 235.815405 times U. Okay, so the difference of mass, which is the mass of products minus the mass of the reactant, will be, if you enter the information that you have there, will be mass of product minus mass of the reactant will be negative 0.18666 times unified mass. Let's convert this into kilograms, because when we are calculating energy, we have to convert it into kilograms. So negative 0.18666 times 1.660540 times 10 to the power of negative 27, and the change in mass will be negative 3.099560 times 10 to the power of negative 28 kilograms. And the energy that is produced based on the mass energy principle is delta M times C squared, or negative 3.09960 times 10 to the negative 28 times 3.0 times 10 to the power of 8, the whole thing to the power of 2. And the energy in joules will be negative 2790 times 10 to the power of negative joules, or in mega electron volts, 174.4 mega electron volts. Okay, this is fission. And now what is happening on nuclear fusion? Is the opposite of it. So what is happening is two smaller sizes atoms are coming together to form a larger one. Okay, so examples of fusion are 2 deuterium, which are isotope forms of hydrogen. So deuterium H12, H12, 2 deuterium are forming a helium-3, helium-2, 3, and neutron and heat or energy. Or fission may happen, or a very common fission reaction is tritium, so H3, again an isotope form of hydrogen, and deuterium are forming helium and neutron and heat. The problem to overcome in fission reaction is to bring the parent nucleus together so that the electrostatic repulsion is overcome and the strong nuclear forces can take over. Nuclear fission reaction require extreme high pressure. High pressure and temperature. High temperature to get them started. Such pressure and temperature are found at the core of our sun. In stars, the nuclei are forced together due to enormous gravitational force involved. In turn, the forces created by fission reaction, fusion reaction, try to explode the star. Therefore, there is a balance between the force of gravity and the forces produced by fusion reaction. Okay, let's see, I will bring a table here or a picture here where it shows the element formation. This is the reaction. So what do you see here is the reaction that is happening in our sun. The main reaction that powers the sun's energy is a series of reactions leading to the formation of helium from hydrogen. And see now how it is formed. You will see that the reaction and the gamma rays, so those are gamma rays, and then you see helium-3, and then finally helium-4 that is produced, and a lot of gamma ray and neutrons that are produced. All those reactions are here, so hydrogen-2, hydrogen-1 are combined together to form hydrogen-2 or deuterium, and gamma ray, heat, and then what is happening is hydrogen-2 and hydrogen-1 are combined together to form helium-3, and then finally 2 helium-3s are forming hydrogen and helium-4. 70% of our matter in the universe is in the form of hydrogen, and in fact it is form hydrogen that all elements are eventually synthesized. And this process occurs on the fusion reaction within the stars. Those reactions will continue until the hydrogen fuel has been mostly completed, done, not existing anymore. As the reaction rate decreases, the gravitational pressure will partially collapse the sun, which will lead to increased pressure in the core. When the pressure and the temperature reaches the critical point, helium nuclei will begin to fuse to produce larger elements. Due to more energetic helium fission reaction, the increased fission pressure will cause the sun to expand the size into a red giant, swallowing the Earth in process. Okay. This is nuclear fission and fusion. Next one will be the radioactive reaction, and we'll continue with the rest of it.